So we want to look at two things today. What are waves? And some equations that are useful with waves. First of all, you might see waves when you go to the beach, and you might not see waves when you go to the beach because you might have your eyes closed. But or you could be at a particularly bad surf beach. But when we're talking about waves, we're talking about that kind of up and down motion where energy is being transferred. Because remember, in physics we have to consider energy usually as one of the main considerations. When you're looking at waves, you'll see them as this up and down motion of water when you're at the beach. But and when you're talking about waves from a non-physics perspective, then you might talk about how the wave goes up and down and you start feeling a bit seasick or whatever. But it's really important to start thinking about the world in terms of physics ideas. So energy is almost always a major player when you're considering the world through the eyes of physics goggles. Here's your physics goggles. They probably look a little bit lame because I'm not a great artist, but put your physics goggles on. Anyway, so waves, way of transferring energy. If you consider the water and you stick something on it, that thing moves up and down. So there's energy that is moving it up and down. But if you are a surfer, okay, I'm not going to draw this very well, but we'll give it a go. Here's a surfboard with a person surfing, sort of a person. They look like they're facing to the left, but really they're facing to the right. Trust me. And as this wave is moving energy, this person who's on the wave here, perhaps it's more as the wave's breaking, they're going to be pushed in a particular direction as they're on the wave that's going up. So as this next section tries to go up, it's going to push the person and they'll fall off and they'll keep going across that way. Okay, good enough. What now? Energy is transferred, but the medium is not. The medium stays roughly in the same place. It shifts up and down, as we've seen, about that equilibrium position. So that's what waves are. You know what waves are instinctively, but we need to look at it in terms of physics. Energy transfer, remember. Now, the equations that can be useful for this, since we're considering waves in water, we'll use this as an example. If you were to put this on a graph axis with, let's say, time there and displacement here, that kind of looks like something you might have seen before in maths. It looks like a sine curve, and in fact it is, or close enough. And there's a few features of this that are particularly useful to identify. One is the wavelength. Okay, wavelength symbol lambda is the distance between two successive points before the wave starts to repeat again. So wave is obviously cyclical in nature. That means it repeats, it repeats, it repeats. Okay, you get the idea. And the wavelength is the distance all the time, depending on how you look at it, before the wave repeats. If you're considering a wave passing through a single point and you're only looking at that one kind of slice, as you see something moving up and down and back again, as that bob, if you like, moves up and down and then back to its original position before it moves up and down and back to its that first up and down and back to its original position, that's one wave will have passed at that point, so one wavelength will have gone through. If you're considering it static on here, then before it starts repeating itself, starts from the top, goes down and up and back again, and then goes down again. That's a new wave starting after that. So wavelength's really important. We've got because we're talking about time in this case rather than actual distance measurement, which is a wavelength. This should really be distance on here when we're dealing with the wavelength. But if we're talking about time, we would talk about this as the amount of time for one period. Okay, so this, if it's time on that axis, we would talk about the time period, the amount of time before one wave repeats. Okay, so the time it takes for the wave to pass before it starts repeating again, that's your time period. There's another one, your frequency, which is the amount of waves passing the point per second. So again, you might be watching at this point here, and you're watching as the wave travels, or if you prefer to, you would talk about the up and down motion as one piece moves up and down and back again. The frequency is the amount of times it goes up and down per second. Okay. Now we've got some formula. Well, there's also the velocity of the wave, which is how fast it's travelling a distance over time, and that's how fast that the energy is propagating. Okay, now the formulas. Those are just some variables. We need the formulas. This is the wave equation, V equals F lambda. Very, very important formula. Will come up time and time again. And we've also got another formula. The frequency is 1 over the period, or you could rewrite that as the period is 1 over the frequency. That's just a rearrangement of the same equation. So the frequency of the wave, how many times per second it goes, if you take the inverse of that, that'll give you how many seconds it takes for one part to pass. Okay, give you an example. If there's 2 waves per second, that's the frequency. And if it takes 2 waves in 1 second, that means it's half a second, which is 1 over 2, or 0.5 seconds for one period. Okay, the period of the wave is half a second. That one's a bit easy to deal with, and you can look at the inverses in your own time to deal with that too. Now, for V equals F lambda, we've seen V is the velocity, the speed of the wave. Okay, wave speed. F is the frequency, which we saw, we were looking at this equation up here, so you could do an alternate form of this equation. V equals 1 over T times lambda, because you're substituting in this, and lambda is the wavelength itself. Okay, the length of the wave, GTH, and I've run out of space on that side. So give you a really simple example. What's the velocity when you have 2 cycles per second and the wavelength is 20 meters long? So that gives us 40 meters per second is how fast the wave is going. And yeah, that's waves and wave equations.